In this next section, we're going to look at what's called compound interest. Now, compound interest is actually used much more frequently in the real world than simple interest is. Simple interest, that formula is still important in a lot of different applications, but when we're talking about savings accounts and even loans and things, the idea of compound interest is really the one that's more prominent and one that's used most often. So compound interest is the interest computed on the original principal as well as on any accumulated interest. So basically what happens is if your account earns interest, they put that interest back into your account automatically. Now, obviously you could take money out of your account or add more money, but let's say theoretically you didn't touch it. Well, then what happens is the next time they compute interest, it's getting computed on a larger amount because you have your original principal plus the first round of interest that already went in. Sorry, excuse me. And this process keeps going over and over and over again. So let's say you have money in an account and you're not going to touch it, right? You put $100 in an account and you're just going to leave it. Well, the first time it computes interest, they're going to put that interest into your account. So now you don't have 100, you have a little bit more than that. Then they compute interest again on this new higher amount. And then they put the interest back into your account. So what happens is that amount in your account continuously grows, assuming, again, you're not taking any money away from it. And you're always computing interest on interest. And this is really how you can grow your money. So many savings accounts pay compound interest. And for example, let's say that you deposit $1,000 in a savings account at a rate of 5%. And let's say that interest is compounded yearly or annually, yearly or annually, same thing. So that is the interest gets computed on a yearly basis and rolled into the principal. How much would be in the account at the end of 3 years? Okay. And again, I just want to make a note. Annually and yearly really mean the same thing. So let's talk about what's happening here. So let's do year one. And I'm going to start with my simple interest formula first. So, or that the calculation for the amount using the simple interest formula. So I know the amount is going to be the principal times 1 plus the rate times time. My principal here is $1,000. Now my rate is 5%. So 5% we can convert to the decimal by moving it 2 spots to the left. So 0.05 in decimal form. And our time here is going to be just 1 year, right? So if interest is computed annually or yearly, it's going to get computed on a yearly basis and then rolled into the principal. So we do it at the end of the year if it says annually or yearly. So our time is going to be 1 full year. So we get $1,000 times 1 plus. Now 1 times 0.05 is just 0.05. This becomes 1,000 times 1.05. And when we go ahead and multiply that out, we get $1,050. Okay, so not too bad. At the end of the first year, you have $1,050. Now we're going to do this for 3 years. So let's say you don't touch your money. You don't, just going to leave it in the account. Well, what's going to happen is that we're not going to compute interest on just $1,000 now, because now you have $1,050 in your account. So we're going to compute the interest on the $1,050. And everything else is going to stay the same, right? It's still the same rate. It's still the same amount of time. 1 more year is going by. And what we're going to get now is going to be $1,102.50. Okay, so your amount is going up again, and actually went up more than it did last time. So if you look at the change from 1050 to 1102, it's going up by $52.50. So not just 50, but a little bit more because your account had a little bit more in it. So let's do the end of year 3. And right now what I'm doing is I'm just using those simple interest calculations we did from the last section. But because I'm doing it over and over again, I'm starting this idea of compound interest now. So I'm using that simple interest formula, but because I'm doing it repeatedly, I'm now compounding it. And this is usually what happens for most accounts. All right, so for the last one, we're going to get about, I'm going to round here, $1,157.63. Okay. So in the first year, you're starting with $1,000 and you haven't done anything. By the end of the third year, you have $1,157. So, and 63 cents. You've made almost $158. And that's just from the interest on your savings account. And again, this is compound interest because what's happening is the interest is not being calculated just on $1,000 anymore. It's being calculated on that new higher amount in your account. So every time we add interest back in, you have more principal. So it keeps growing and growing. Again, assuming you're not taking any money out of it. Now, this is good. We can do this, but it's pretty tedious. So if I want to do this for a long period of time, then this is kind of a pain to do over and over and over again. So we do have a shortcut formula that we can use when we're doing compound interest. So there is a formula we can use to make this quicker. If you deposit P dollars at rate R, so P is still your principal, R is still your rate. We're doing compound interest. A is still your future amount, and T is still years. So those have all the same designation we're used to. We can use this formula here to find the amount when we're compounding. Now, N represents, and this is important, so this is new. N represents how many times interest is paid or compounded per year. We often call this the compounding period. So compounding, you can also think of it as just calculating, right? So how many times you do this calculation, that's what we're asking here. Now there's a couple keywords here. So when interest is compounded or paid once per year, we say that it's compounded annually. The N value is 1. When interest is compounded twice a year, we say it's compounded semi-annually. So N is 2. So that would be every 6 months, right? If it's twice a year. When N is compounded 4 times a year, we say it's compounded quarterly. So your N is equal to 4. So if there's 12 months in a year and we're doing it 4 times, 12 divided by 4 is 3. So every 3 months you would be doing this. And we can even have monthly compounding when N is 12. So you do this kind of interest calculation every month. And you can even have daily compounding, either N being 365 or 360 if you're using a banker's year. So you're adding in interest at the end of every day to the account. So there's different ways you can do compounding, and different banks will have different accounts that compound differently. So it's one thing to note as well how your money is being calculated, how that interest is being calculated. In general, the more you're compounding, the faster interest is growing. So let's say you deposit $2,000 into a savings account. You have a 6% interest rate. We're going to find the amount of money at the end of 3 years, subject to interest compounding once a year. So I'm going to use my formula here. So again, I see that we're compounding, so I know I'm doing compound interest. So my P here is 2,000. My rate is 6%, which is going to be 0.06, right? Moving that decimal spot 2 points left. I'm going to do this for 3 years. So my T is equal to 3. Now the different thing is the compounding. It's compounded once a year. So if it's compounded once per year, this is called compounding annually. Your N value is 1. So I have my formula. And I'm just plugging in all my values. Now, when N is equal to 1, your formula actually simplifies quite a bit. And it becomes just this, right? Because that N here and the N here are going to just cancel out. So you can also use this formula here, specifically when N equals 1, and this is what your book does. I actually just like to have one formula so I don't have to keep memorizing formulas over and over again. So I like this general formula because it does any sort of compounding that I need. Notice that as I'm simplifying, I'm working inside the parentheses first. So you're still following the order of operations, working in that parentheses, kind of cleaning it up in there first. Now you're going to do your exponent. So before I do my multiplication, you do need to do your exponent first. So I'm typing in 1.06 to my calculator, and then I'm going to use my little up arrow here and do 3, and that will do a cube for me. And I'm just going to use all the decimal places, which is really important. I'm going to multiply that by 2,000. So I get about $2,382.03 if I round to 2 decimal places. Let me just move this up a little bit for you guys to see. Now to answer part B, if you want to find the interest, okay, so your interest is the same thing as taking that final amount and subtracting out the original principal. So my amount here was $2,382.03. My original principal was $2,000. So my interest is about $382.03. And again, I did round here, right? So I guess it is approximate because I did have to round my answer. But you can see the account made almost $400 in those 3 years. All right, let's do a couple more examples. So here you deposit $7,500 into a savings account that has a rate of 6%. The interest is compounded monthly. How much will you have after 5 years? So again, set up that formula. So my P here is 7,500. My R is 6%, which is going to be 0.06 once I move my decimal point. My T here is 5 because it's 5 years. Again, T is still in years, so if you have something less than a year, just be careful. So you could use a fraction there or a decimal. Now the last thing is the compounding. So here's the new idea. If it's compounded monthly, so if you forget, go to your page before, and I have the majority of them listed here for you, so the most common ones. So if it's monthly, it says N is 12. Okay. So basically is how many times a year do you do this calculation? So if you're doing it monthly, you're doing it 12 times a year. So our N is 12. And now I'm just going to fill everything in. So I'm just filling in my values, and I'm going to simplify using Pemdas. So I'm going to start here and just do that 0.06, divided by 12. So I get 1 plus 0.005. And then here, 12 times 5 is 60. And 1 plus 0.005, that's pretty quick. And now I do want to do my exponent first. So if your calculator can do everything at once, then that's fine too. But if you have a calculator that can only do one step at a time, make sure you do your exponent first. I'm going to use that little up arrow here, and then I can type an exponent of 60. And I get 1.348850,153. Multiply that by 7,500. And I get $10,116 and about 38 by round. B, find the interest. So I'm going to take my final amount and subtract my original principal. So I have $10,116.38 minus that 7,500. And let's see, I get about $2,606.35. $16.35. So again, not too bad. So for 5 years at 6% interest, compounded monthly, we're earning over $2,500 just in interest. So that's like free money if it's your savings account, right? If you have a loan, not so much good for you, good for the bank. But if you have a savings account, this is all free money. So it's good to take advantage of it. One thing you'll notice is that typically the more you're compounding, the more interest you're calculating. So if you can compound monthly versus yearly, that's going to give more interest. If you can compound daily versus monthly, you're going to get more interest. So the more you compound, it means the more often you're doing that interest calculation and you're putting that money back into the account. So the principal is just growing faster. Now, there is actually a way to do something called continuous compounding. And there are some institutions that do continuous compounding. So this occurs when the compounding periods increase indefinitely. So you're compounding interest every trillionth of a second, every quadrillionth of a second, etc. So just you're continuously calculating interest. As n increases to infinity, what ends up happening is this right here actually approaches the irrational number e. So those of you are probably more familiar with the number pi, but we also have other very common values that we use in mathematics, and one of them is e. So this approaches e as we start compounding more and more frequently, moving towards infinity. So our formula gets simplified, and it actually becomes this instead. P is still your principal, R is still your rate, and T is still your time. This E value, you should be able to find it on your calculator. A lot of calculators have it pre-programmed in, but if you can't find it, then you want to use this for E, and this would be fine. Okay, don't round, don't use just 2.7 or 2.71 or 2.72. So don't round, use all these decimals. So when we have exponents, rounding errors really add up fast. So the more decimals you can use, and that's why I did it up here too, the better your answer is going to be. All right, so you decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first account pays 7% compounded monthly, and the second account pays 6.85% compounded continuously. Just making a little bit of notes for myself here. Which is the better investment? Now, again, you're investing your money, so the interest is going back into your account. So you want to make the most interest here, right? So think about what's happening. If this was a loan, we don't want to make the most interest. If it's a savings account, we do. So you want to think about, are you getting the interest or is the bank getting the interest? So here, if we're investing, then we get the interest. All right, so let's go ahead and do these out. So the first one is a regular calculation. All right, so let's see. Our P is going to be 8,000. Our T is 6 because it's for 6 years. For this one, our rate is going to be 0.07, right? Moving that decimal point over. And if we're compounding monthly, we're doing that 12 times a year, so our N is 12. So we have 8,000. 1 plus 0.07 or 12 to the 12 times 6. All right, so again, I'm going to use my calculator here. I'm going to work order of operations. I'm going to do 0.07 divided by 12 first. I get a lot of decimals, which is fine. I'm also going to do the adding to 1 right now, just kind of finish cleaning up that inside piece. So I get 1.005833333, and then 12 times 6 is 72. Now I'm going to go ahead and do my exponent here. So I'm going to raise this to the 72nd power. I get 1.520105504, and I multiply that by 8,000. So my final amount here, rounded to 2 decimals, is $12,160.84. Okay. Again, notice I'm using so many decimal places. That is really, really important in this section, particularly once you get into exponents. If you start having exponents anywhere, you need to use lots of decimal places because exponents just cause errors to blow up really fast. So use all those decimals that you can, whatever your calculator will give you. All right, now for the other option, let's use a different color. We're going to compound continuously. So my rate here is going to be 0.0685. Again, moving that 2 spots to the left. But because I'm compounding continuously, I'm going to use this new formula. So I have 8,000 times e to the 0.0685 times t is 6. So again, before I go too far, I'm going to clean this out. I'm going to do my exponent here and simplify that multiplication. So 0.0685 times 6. So I get 0.411. Then I'm going to do my exponent. Now, if you have a more high-end calculator or the calculator app, you can see I have E right there. So I'm going to hit that second button first and then this key so that I can use the little part here. So I hit second and that LN button, and then I can type in 0.411. Using all my decimals and multiplying by 8,000. So rounding to 2 decimal places, about $12,066.60. Now, if you don't have an E on your calculator, that's okay. Just go back up here and use this value here. So you would do 2.718281828 and raise that to that 0.411. So you can do it more manually and you'll get almost the same answer. So you maybe have some slight rounding error at the end here, but it's going to be very close. So if you don't have the E key, that's okay. Just use this value here anytime you see it. All right. So if I compare which one is the better investment, well, in this case, the better investment is this one, right? So I'm going to make a little bit more money here. I make almost $100 more. That adds up. So this is more. So this is the better investment here. Now, continuous compounding is sort of the best compounding because you're doing it most frequently if you're talking about your own personal investments. But the 7% versus 6.85% makes a bigger difference. So even though continuous compounding increases your interest, faster in a way because you're doing it more frequently, that rate of 7% is just big enough where it actually is better over time. So it's not just the compounding, it's also the interest rate. So those two things together, plus the length of time that you have your money in the account for, is really going to affect your better option. So it's good to kind of look at everything before you make decisions.